Hi everyone, welcome to Bite Size Med, where we talk about quick, bite-sized concepts in basic medical sciences for study and rapid review. This video is on how the lungs regulate acid-base balance. Just a quick recap. There are three regulatory systems of acid-base balance: buffers, the lungs, and the kidneys. The Henderson-Hasselbalch equation gives a pH of the solution. That's pH equals pK plus the log of the concentration of base over acid. If there's an increase in the hydrogen ion concentration, the pH reduces, and there's acidosis. If there's a lower hydrogen ion concentration, the pH rises, and that's alkalosis. The normal pH of blood is around 7.4. The most important buffer pair is the bicarb carbon dioxide pair. They have a pK of 6.1, so the pH is equal to 6.1 plus the log of the bicarb concentration over 0.03 into the partial pressure of arterial carbon dioxide. This carbon dioxide level is what the lungs regulate. Respiration is controlled by the central nervous system to maintain a constant arterial oxygen and carbon dioxide level. It's regulated by central chemoreceptors, which are in the brainstem, and peripheral chemoreceptors in the carotid and the aortic bodies. The central chemoreceptors respond to changes in the hydrogen ion concentration in the CSF, and the peripheral receptors to changes in the partial pressure of arterial oxygen levels, also the hydrogen ion concentration and the pH of blood. The carbon dioxide levels in the blood would depend upon how much is produced and how much is eliminated. It's directly proportional to the cellular metabolism rate, which increases carbon dioxide production, and inversely to alveolar ventilation, which controls carbon dioxide elimination. So if there's increased cellular metabolism, there's more carbon dioxide. And by the Henderson-Hasselbalch equation, more carbon dioxide means low pH, acidosis. If there's increased alveolar ventilation, there's more carbon dioxide elimination. So there's an increase in the pH, alkalosis. The brainstem has a chemosensitive area near the center of inspiration. That responds to a change in the hydrogen ion concentration in the CSF. Hydrogen ions from the blood cannot cross the blood-brain barrier to reach the CSF, but carbon dioxide can. So if the carbon dioxide levels in the blood are high, it crosses the blood-brain barrier, combines with water to form carbonic acid, which then dissociates into the hydrogen ion and the bicarb ion. These hydrogen ions trigger the inspiratory center, which increases alveolar ventilation. So there's removal of the excess carbon dioxide, lowering the hydrogen ions and normalizing the pH. This effect fatigues in 1 to 2 days when the kidneys take over and increase hydrogen ion secretion and increase bicarb reabsorption. So the equation tells us everything we need to know. pH equals pK plus log of the concentration of bicarb over 0.03 into the partial pressure of arterial carbon dioxide. If the PaCO2 is high, the pH will lower, so the kidneys compensate by increasing bicarb. That increases the pH towards normal. If the PaCO2 is low, the pH will be high, and the kidneys compensate by lowering bicarb, so the pH reduces towards normal. There are 4 primary acid-base disturbances, 2 respiratory and 2 metabolic. So that's metabolic acidosis and alkalosis, and respiratory acidosis and alkalosis. If the primary change increasing the pH is a fall in the partial pressure of carbon dioxide, that is respiratory alkalosis. While if the pH falls from a rise in partial pressure of carbon dioxide, that is respiratory acidosis. The change in pH from anything other than a change in the PaCO2 is metabolic. Respiratory acidosis is caused by hypoventilation. So there's reduced ventilation, meaning there's carbon dioxide retention. So the PaCO2 rises. And by the equation, the pH will fall. So the kidneys compensate by increasing bicarb. There's new bicarb formation and there's increased hydrogen ion excretion. And that is metabolic compensation for respiratory acidosis. Respiratory alkalosis can be caused by hyperventilation. When there's excess ventilation, there's more carbon dioxide washout. So the PaCO2 will reduce. And by the equation, the pH will increase. So the kidneys compensate by lowering bicarb. So there's reduced synthesis and reabsorption of new bicarbonate and reduced hydrogen ion excretion. And that is metabolic compensation for respiratory alkalosis. Changes in pH of blood are detected by the peripheral chemoreceptors in the carotid bodies. If the pH is low from metabolic acidosis, it stimulates these receptors, which stimulates the centers of inspiration, increasing ventilation. So there's more carbon dioxide washout. And that is respiratory compensation for metabolic acidosis. Similarly, in metabolic alkalosis, when the pH is high, they reduce ventilation, so it retains carbon dioxide and lowers the pH towards normal. And that is respiratory compensation for metabolic alkalosis. So that is how the lungs regulate acid-base balance. If you found this video useful, give it a thumbs up and subscribe to my channel. Thanks for watching, and I'll see you in the next one.